Challenge problem number 12 is a really interesting problem because it involves Gauss's law and it involves Maxwell's equations, just in the fact that it involves Gauss's law, but that this kind of interesting wrench was thrown into the problem of that we're now in flatland, which is in 2 spatial dimensions instead of 3. So instead of an electric field like propagating out through an area and taking that dA, or the total area around a charged object or surface or point charge, it's now a kind of squished 2-dimensional version. So that makes the problem pretty interesting. So part 1 asks, if we were in flatland, derive an expression for the electric field due to a point charge. So normally the Gaussian surface would be a sphere with the radius r. So you would use, for this dA here, you'd use the expression for the surface area of a sphere, which is, I don't remember it offhand. It's 4/3 pi, that's area, volume. But anyway, instead of using that, because the sphere is squished and we're in 2 dimensions, no matter where you are, you're always going to be this perfect distance r, that radius, away from the point charge. So you can just say, oh, well, this is the circumference of a circle, obviously, so it's just 2 pi r, or pi d. So that's what you put in for area. So when you're solving for E, you just have Qn over E naught, and then also divided by area. So E is equal to Q divided by E naught times 2 pi r. Now, this would normally be the surface area of that sphere, but because it's squished, it's just 2 pi r. So it's an interesting way to think about it. So part 2, similar to part 1, because the Gaussian surface is squished, and it's a line of charge, so it's infinitely long. But if you think about one part of it, this section with length L and distance r away from the line of charge, it would normally be a cylinder, a perfect cylinder with the line of charge going straight through the center, and every surface of the cylinder being that distance r away. But because it's squished flat, it's squished into a perfect rectangle. So we only have to worry about L as the area, and we don't have to worry about R because, or we don't even have to consider R because it's perfectly perpendicular to the surface, which is the line of charge. So we don't include this in the expression. Just include L because that's where the electric field is kind of going up through. So we know that lambda is equal to the linear charge density, or the amount of charge per unit length of the line of charge. So the expression, we can just say this is 2L is the area. Normally it would be the area for the outside of the cylinder, but we can just replace it by 2L because it's squished. So we know that E is equal to Q over E naught times 2L, and we also know that Q divided by L is just equal to lambda, so we can just say E is equal to lambda over 2 epsilon naught, which is really nice because it's a really small, concise expression. Actually, both of these are. It's kind of amazing how how Gauss's law especially can just take something really complicated and give you an expression so easily. But yeah, so that's how you do it.